This is William Dillon from the Department of Electrical Engineering at the University of Texas at Arlington. We now begin our second lecture on complex numbers. Now we'll look at phasors and simple harmonic motion. We begin with a look at the sinusoidal function. As you can see, we've got this wavy line, the red line that you see in this little plot, and that is a sinusoid. All sines and cosines are considered sinusoids, and the sinusoidal function in the time domain here, since we're really describing a time varying function, then our angle varies as we move along in time. So omega, this term you see right here, is the radian frequency of the sinusoidal function. It's in radians per second, where the radian is an angular measure. Remember, they're about 57.3 degrees per radian, and you multiply that by t in 10 seconds and you get an angle. So omega t makes an angle, and phi is an arbitrary offset. So it's the cosine isn't starting exactly at its peak here. Okay, so this makes it very general when it comes to the angle, because these voltages and currents that we're going to be measuring and calculating as sinusoids can have almost any angle. And so we have to be completely general with that. Notice that this is that there's no offset. Our function is oscillating around 0 magnitude. So the sinusoid has a positive value and a negative value, and it does this cyclically, and the positive peak is equal to the negative peak in magnitude. So the sinusoidal function basically has three parameters of interest to us: the peak value of it, the radian frequency, omega, and phi, the offset from, or the phase shift as some of us would call it, from 0. Okay, so that's the definition of our function. As you can see in this, on the x-axis down here, on the x-axis we're looking at the angle in radians. Okay, so that's from 0 out to 6.28 is one complete cycle of this. Now, one of the first things we must do is that we must learn to convert this sinusoidal function in the time domain to a phasor. So we'll go into the frequency domain when we do that. So let's rewrite our function. As you saw in the previous view, where we described v as a function of t, it had a peak value, it had a frequency, and a phase shift. But this doesn't say cosine, does it? Instead, it says RE. That means the real part of a complex number. In the curly braces here, we have a complex number. It's expressed in exponential form, though. It's e, the base of the natural logarithm, raised to an exponent, j, times the angle. This time, our angle is a function of time. Okay, so this expression is exactly equivalent to the time-varying function we saw on the previous page. They mean exactly the same thing. They're both time functions. Let's work on this a little bit. We know that when we have an exponential form like this, when I have a sum of two exponentials, or two exponents that is, then I can write that as a product of two exponentials. So e to the j omega t plus j phi can be written as e to the j omega t multiplied by e to the j phi. So I can write it as a product. That's good. Then, what are we going to do with that? To go to the phasor domain, we'll call it a transform. We're going to go from the time domain to the phasor domain. And here's how we do it. The mathematics is pretty simple. What we'll do is set t equal to 0. Okay, t is going to become 0. So this first term, e to the 0 power, is 1. Okay, so that takes care of that. And that leaves us with a complex number, e to the j phi. See, this is no longer a function of time when we do this. And so I'm really freezing this at t equals 0, right? And then re means take the real part of. So the second thing we do is remove the restriction, that we are only looking at the real part of this. Okay, so that means that we are going from the frequency domain down to the phasor domain. And so we'll call it the phasor now. And so now our voltage, instead of being that wavy sinusoid, is now represented by a complex number. It's got a peak value, we'll talk more about that later, times e to the j phi, which e to the j phi is kind of like saying angle of theta, okay? And so that's e to the j phi is a complex number, magnitude 1, with an angle of phi. Now, a common way to describe a phasor variable is to write a capital letter with a tilde on top. That's how many textbooks do this. Some use just boldface type to indicate a phasor as if it were a vector, but we'll use this notation for now. So V with a tilde, capital V with a tilde, indicates phasor variable. And to express it more mathematically, it's got a magnitude of V sub m at an angle of phi. And that can be radians or degrees. Here's a picture of it on the complex plane. Imaginary axis, vertical, real axis is horizontal. And there's our phasor. Okay. Now, we can also express that in rectangular form. And so if we took V max times the cosine of phi, we get the projection on the real axis. If we took V max times the sine of phi multiplied by j, we get the projection on the imaginary axis. So now we can represent our voltage as though it were a complex number. But we have some other rules that we have to use with that, which will be developed later.